Hello everyone, welcome to my presentation with the title on the combined effect of internal and external intermittency in turbulent non-premixed flames. My name is Gauding and this is a joint work with my colleagues from Korea in France and with my colleagues from the Institute of Combustion Technology in Germany. I will start my presentation with an explanation why intermittency is relevant for turbulent jet flames. Then I will introduce the direct numerical simulations on which the analysis is based. Then I will introduce the concept of the turbulent non-turbulent interface for jet flames. I will use this to quantify the structure of the TNTI, and then we will assess the impact of external intermittency on small-scale turbulent mixing. Intermittency in general describes a stochastic process that is characterized by very strong but also very rare events. Intermittency occurs in a turbulent jet flame at different scales. At the smallest scales, we have internal intermittency, which is created by the vortex stretching mechanism of turbulence, and this is important for the molecular mixing at the smallest scales. On the other hand, we have external intermittency at the edge of the flow where the turbulent and the non-turbulent fluid meets. There we have a very thin layer, and this layer is called the turbulent non-turbulent interface. This interface is important for the entrainment of oxidizer into the jet fuel, and this corresponds to the mixing at the larger scales. However, the situation is more complex in turbulent non-premixed flames. In most hydrocarbon flames, the surface of the stoichiometric mixture is close to the turbulent non-turbulent interface. Here in this figure, we see an illustration of a turbulent non-premixed flame. We have a fully developed turbulent core, and then we have the turbulent non-turbulent interface in red, which is the boundary of the turbulent envelope. Then we have the layer of stoichiometric mixture in green, and we see indeed that both layers are close to each other, and here we even have intersections. And the question that we will address in this presentation is what is the effect of external intermittency, meaning fluctuations at the turbulent non-turbulent interface on turbulent mixing in turbulent non-premixed flames. This question is particularly important for flamehead models because gradient trajectories of the mixture fraction field oftentimes cross both the zone of stoichiometric mixture and the turbulent non-turbulent interface, and this is especially the region where most of the chemical reaction happens, and therefore it is important to understand what are the features of the turbulence in this area. The analysis is based on a planar, temporally evolving non-premixed jet flame. We have used a higher order numerical scheme. We have a diluted methane air flame, finite rate chemistry, 30 species, 102 reactions. We have a relatively high stoichiometric mixture fraction of 0.45, and the jet Reynolds number is 4,500. Here we see a visualization of the computational domain. The streamwise direction is x1, the cross-stream direction is x2, and then the jet evolves in time in the x3 direction. Before we start with the analysis, I would like to briefly visualize the effect of external intermittency in turbulent jet flows. Here we see the field of the scalar dissipation rate at the center plane. We have regions of very high local activity of the scalar dissipation rate. This is characteristic for internal intermittency, but the field is overall fully turbulent. When we move from the center to the edge of the flow, we have local patches of no activity directly adjacent to patches of very strong activity, and this is a characteristic footprint of external intermittency. And the question that we will address is what is the effect of this very specific flow structure on turbulent small-scale mixing. In the next step, we need to define the position of the TNTI. We do this based on a threshold of the entropy field. When the local entropy is larger than a certain threshold, we define the flow as turbulent and otherwise as non-turbulent. A precise and accurate definition of this interface is particularly important in turbulent reactive flows, because when we have local heat release, the viscosity increases, and at the same time, this increase in viscosity damps the turbulence. and therefore it is important to have a criterion that is able to account for this effect. The position of the TNTI is relatively independent of the specific threshold because at the TNTI we have a steep gradient in the entropy field, and the consequence is that the volume within the turbulent envelope is relatively independent of this specific value. Therefore, we can conclude that we have a criterion where the position of the TNTI is relatively robust. After having defined the position of the turbulent non-turbulent interface, we can quantify external intermittency by the intermittency function. This intermittency function is 1 when the flow is turbulent and 0 otherwise. When we take the ensemble average of this intermittency function, we obtain the intermittency factor. And this intermittency factor in our flow is only a function of time and the cross-stream coordinate x3. And the intermittency factor gives us then the probability that the flow at a certain cross-stream position is turbulent. This is shown here in the right figure. At the center plane, the flow is fully turbulent. Then the intermittency factor is 1. When we go to the edge of the flow, we have mixing between the turbulent flow from the core and the irrotational flow from the outside. And then the intermittency factor decreases towards 0. The intermittency factor does not provide any information about the structure of the TNTI at different scales. To obtain this information, we introduce the intermittency structure function, which is defined as a second-order moment of the indicator function at 2 different points separated by the distance r. In a free turbulent shear flow, we have 3 different options for the location of these ending points. Either both of them are inside the turbulent envelope. One point can be inside the turbulent regime, while the other point is already outside of the turbulent regime, or both points can be outside of the turbulent envelope. And next, we will show that this intermittency structure function quantifies the geometry at the TNTI at different scales in the flame. When we normalize the intermittency structure function, we can quantify the probability that both ends of the structure function are within the turbulent envelope. The center of the jet is fully turbulent, and therefore this probability is close to 1. This changes when we move to the edge of the jet. Here the probability is only 1 at the smaller scales, which are closely correlated, but then it decreases towards the larger scales. And this decrease quantifies the size of coherent turbulent structures at the TNTI. Another information that is contained in the intermittency structure function is the surface density. When we take the limit r to 0, we obtain a one-dimensional surrogate of this surface density. The surface density is shown in this figure as a function of the cross-stream direction. And we see that we have here a very distinct maximum, and this maximum decreases in value while the jet spreads over time. To quantify turbulent mixing in the jet flame, we introduce the nth order structure function of the mixture fraction. In the small scale limit, for this structure function, we have a theory which was developed by Kolmogorov, Ubukov, and Korzen, and this theory essentially postulates that the structure function depends on the mean value of the scalar dissipation. However, it is well known that because of intermittency, the KOC theory is not valid for higher orders. Therefore, in this work, we propose a modified approach. To derive this modified approach, we introduce a Taylor series expansion of the structure function in the small scale limit, and then we make the assumption that the molecular diffusivity is statistically independent from the gradients of the mixture fraction. This assumption can be justified by the picture that the molecular diffusivity changes due to heat release and mixing, while the gradients of the mixture fraction are created by the vortex stretching and foiling mechanism. When we combine these two equations, we obtain an analytical solution for the structure function in the small scale limit, and the essential difference to the Kolmogorov theory is that we propose that the structure function scales with the nth moments of the scalar dissipation rate. Let us now test our modified scaling approach. First, we look at the left at the conventional KOC scaling. We have here the second order structure function at different distances from the center plane, and we find a good collapse which confirms the KOC scaling. This is surprising because the jet is affected by internal and external intermittency, shear, as well as inhomogeneity and anisotropy. However, for the higher orders, we have no collapse, meaning that the KOC scaling is clearly not valid. On the right, we have our modified scaling approach, where we renormalize the structure functions with the higher order moments of the scalar dissipation rate to account for intermittency. And we see that we have a perfect collapse of the higher order structure functions in the small scale limit, which validates our scaling approach. Internal intermittency can be in general quantified by flatness factors because the flatness characterizes the far tails of the underlying PDF. And we introduce the flatness factor of the scalar dissipation and also the flatness factor of the fluctuations of the mixture fraction field. Here on the left, we see these flatness factors as a function of the external intermittency factor. Here at 1, we have fully developed turbulent flow, and in this direction, we approach the edge of the flow. And at the same time, we see that both intermittency factors, the one of the scalar dissipation and the one of the mixture fraction, increases. And this increase represents a signal that is more and more intermittent, because an increase of the flatness means that the PDF of the scalar dissipation and of the mixture fraction has more and more stretched exponential tails. So that we have found here a coupling between the external intermittency factor and the internal intermittency. At the same time, we can define conditional flatness factors that only account for the turbulent portion of the flow. That are the two dashed lines here, and we find that these conditional flatness factors are relatively independent of the external intermittency factor. That means we have within the turbulent regions a rapid mixing. Structure functions also have an inertial range scaling exponent. This is zeta p, which is characteristic for the interscale transport of turbulence. Here in this flame we have a relatively low Reynolds number, so we don't observe a well-established inertial range, and therefore we compute this scaling exponent by the method of extended self-similarity. Here we see the scaling exponents for different cross-stream positions. We have the order P. We see the analytical Kolmogorov-Ubokov-Korsin scaling, and we have a log normal model, which is usually a good solution for homogeneous isotropic turbulence. The difference between the KOC scaling and the log normal model accounts for internal intermittency. And we see that the scaling exponents at the center are more or less in agreement with this log normal model. However, when we move from the center to the edge, we see an additional departure from this model, and this departure is due to external intermittency. To support this claim, we show in the right figure the relative scaling exponents as a function of the external intermittency factor. And we see indeed that independently of the order, when we move from the center to the edge of the flow, we have a decrease of the scaling exponents, which is related to an increase in intermittency. And this figure gives us a clear indication for the coupling of external intermittency and internal intermittency. Let me briefly conclude the presentation. We have analyzed a turbulent non-premixed jet flame in the context of external intermittency. By analyzing structure functions at different crosswise positions, we have shown that external intermittency strongly affects small-scale statistics such as those of the scale dissipation. From that, we have concluded that there is a strong interscale coupling between external intermittency at the large scales and internal intermittency at the smaller scales. This interscale coupling is not universal because it depends on the large-scale features of the flame. This has certain implications for mixing and combustion models because it poses certain constraints for models that were developed in the context of homogeneous isotropic turbulence by assuming universality. Okay, thank you for your attention.